So today's video is going to look at another way that we can approximate areas under curves. And you might say, well, why do we even need to bother with our approximations? Aren't we going backwards? Well, there's two cases where we can't find the exact value of a definite integral. The first, if it is a function that we don't have any antiderivative rules for, and you have two examples of them there. In both cases, if you tried to do a u substitution, there'd be no way to get what we needed for a du. So in those examples, we couldn't find the exact area under the curve, so we would have to do an approximation. Another is if your situation arises from collecting some type of data, maybe in an experiment or something. Well, you might not have an actual function that corresponds to that data that you've graphed. So therefore, we can only approximate the area that's under that curve. Now, we've already seen a few things that can be used to approximate the area under curves when we did our Riemann sums earlier on. In general, remember what we did is found the width of our interval, where we did b minus a over n, where b is where the interval ends, a is where it starts, and n is the number of rectangles you want to split it into. And then we multiplied that by our function evaluated at some reference point in each of our intervals that gave us the height of our rectangles. We started out, we looked at doing, say, left-hand endpoints here, where we picked the left-hand endpoint in each interval to determine the height. We also saw right-hand endpoints to help determine the height. And then we've also seen midpoints, where we took the midpoints of the interval to find the heights. So those are three ways we've already seen. We will do a new way today. Okay? And here's the three together so you can see a visual of them. Okay, and there's just your midpoint. Again, remember your midpoint. It's really just whatever's the middle of your interval. If you had from like 1 to 2, you'd use 1.5 as your midpoint. The new one we're going to see today is called the trapezoidal rule. And we'll see why it's called the trapezoidal rule in a second. In reality, what you're doing is you're averaging your left-hand endpoint approximation and your right-hand endpoint approximation. When we do that, we will end up getting this, and I'll show you where we're getting this from in a second. What this is saying is we'll end up with our width divided by 2, and inside we'll have f of x0 with a 1 in front. Then we'll have 2f of x2s, or 2f of x1s, 2f of x2s, and we'll keep having 2 in front all the way until the second last one. Our last thing, f of xn, whatever the last one is, will again have a 1 in front. And here's why that is. If we look back at our picture, let's start with the left-hand endpoints. Our left-hand endpoints will have x0, x1, x2, and x3. So from that, we will get a f of x0, f of x1, f of x2, and f of x3. When we look at our right-hand endpoints, we use x1, x2, x3, and x4. So we'll have f of x1, f of x2, f of x3, and f of x4. So the delta x is coming from the fact that we just had delta x out in front for each of them. Then if you add all of your f of x's, notice we just have one f of x0. We're going to have two f of x1s. We'll have two f of x2s. We'll have two f of x3s. And then we only have one f of x4. So that's like our xn in this case. So that's what we have when we'd add them together. But when you take an average, you divide by 2. Well, that's like multiplying by half, and that's where that 2 comes from out front. So that's where our equation from this page is coming from. So we've got, basically you have your width, your b minus a over n, divided by 2, because that's really the 2 from averaging them. And we'll look at why it can be thought as the trapezoid rule also in a second, and that's the name we'll use for it. So you can pause the slide and copy it down. Here's your formula in a nice, neat version. And here's why it's called the trapezoid rule. Well, this part I'm outlining in blue, that would have been this rectangle with a right-hand endpoint. The part I'm outlining in green would have been our rectangle in the left-hand endpoint. When you average them, it should be the area that's exactly in between. Well, the area that would be exactly in between would be tacking on to the green section half of the extra part in the blue. Well, half the extra part in the blue would be this triangle. So when you tack that onto the green, that becomes a trapezoid then. That's why it's called the trapezoidal rule. And here is why you could get your formula from thinking of it as trapezoids. Well, each base here is delta x. That's why we have the delta x out front. When you turn it sideways to think of your trapezoids, that's like your height, because your area of a trapezoid formula is 1/2 the height times base 1 plus base 2. So we get 1/2 times our height, delta x, and in our first one, this is our base 1, this is our base 2. So we have f of x0 plus f of x1. Well, in our second one, we'll again have 1/2 delta x. Our bases are now f of x1 and f of x2. And we keep going all the way to the end, and just like before, notice f of x0 only showed up once, f of x4 only showed up once, and everything else showed up twice. That's why all the middle stuff gets 2's in front of it. So the short story is your trapezoidal rule, you'll do 1/2 times your width, and then inside the parentheses, the first x value and the last x value, you'll just have f of those once. All the ones that are in the middle, you'll have f of those with a 2 out in front. And it might be easier to see if you turn the graph sideways that they are, in fact, trapezoids. So let's try an example. Let's see if we can approximate the area under the curve 1/x from 1 to 2, and we're going to use n equals 5, so 5 rectangles. So first let's find our width, b minus a over n, so 2 minus 1 over 5 will give us 1/5. So our x0 is going to be 1, that's where we started. x1 we'll just add our width on, so we'll have 5th is the same as 0.2, so we'll have 1.2. x2 will be 1.4. x3 will be 1.6. x4 will be 1.8. And x5 will be 2.0. So for our trapezoidal rule, we'll have 1/2 times our width. Then in parentheses, you'll have f of x0, because that only showed up once, so we'll have f of 1. Plus 2 of our x1s. So we'll have 2 times f of 1.2. Plus 2 times f of 1.4. Plus 2 times f of 1.6. Plus 2 times f of 1.8. And now our last thing, remember there's only one of them, so you'll have f of 2. And now this is something we're going to put in our calculator. We'll have to make sure we start with a new document, and we'll put in F1 the function we're working with, the 1/x. And then we'll be able to type exactly what we see here in a calculator page. So we'll go to our calculators now, and we'll start out, let's go to a graphs page. And in our graphs page, we'll put in 1/x. And then we'll add a page and go to a calculator page. And we'll put exactly what we saw on the previous, on the slide. So we had, now if we want to do a shortcut, we had 1/2 times 1/5. So we can just go ahead and put that in as 1/10 if we want, so we don't have to type two things in. If you want to do it separately, you always could do that as well. Then we'll have our parenthesis. then we only have one f of 1. Now remember, you can go variable and just select f1 so you don't have to type it in. Plus, we'll have 2 at 1.2. Plus 2 of them again at 1.4. Plus 2 of them again. And again, I'm just hitting variable to get the f1 each time so you don't have to type the whole thing in. So 2 of them at 1.6, 2 of them at 1.8, and then remember we only have 1 of them at 2. So our end ones only get 1 of them. Now, just like we were doing this before, double check, make sure you closed all your parentheses and everything. That you got the 2's in front of the correct things. And we get this back. So if we go back to this page, this just ended up equaling 0.6956349206335. And it didn't tell us to round or anything, and it's just an approximation, so we'll keep that. Well, now let's see what we would have gotten with the same thing, but with the midpoint rule. So we already knew our width was 1/5. Then we've got to do f of each of the midpoints of our intervals. Well, we know we go from 1 to 1.2, 1.2 to 1.4, 1.4 to 1.6, 1.6 to 1.8, and 1.8 to 2. So our midpoints will have 1.1, 1.3, 1.5, 1.7, and 1.9. So in here we'll have f of 1.1 plus f of 1.3 plus f of 1.5 plus f of 1.7 plus f of 1.9. And we'll put this in just like we did the other one on the calculator. So we'll put in our 1/5. And we'll do our f1 of 1.1. Then we'll do it for 1.3. Make sure you're closing your parenthesis and putting your plus each time. 1.5. 1.7. And 1.9. Take a second and double check that you plugged everything in correctly. And we get this. So we'll copy that over. So we had 0.691907885716. And that's what we get for our midpoint rule. Here's a visual of that midpoint rule. And let's just see now, because this one we actually know how to find the exact value. 1 over x, its antiderivative is the natural log of absolute value of x. And we'll do it from 1 to 2. So this is just natural log of 2. We can just put 2 because absolute value of 2 is 2. Minus natural log of 1. Well, natural log of 1 is just 0, so we get just natural log of 2. Well, if we plug that in our calculator, we get about 0.693147 or so. Our midpoint rule, remember we got 0.691907 and some other stuff. Our trapezoidal rule, we got 0.695634 or so. So the midpoint's just about 0.692, and we have 0.6956 or so for the trapezoid. Well, our actual answers should be 0.693. So notice in this case, the midpoint rule was a little bit closer than the trapezoidal rule. Now, if you want to find the actual values, the amount that it's off by the error, this is just saying the error of the trapezoidal rule is taking our exact value and subtracting off our trapezoidal value. When our trapezoidal value was too big, so that's why it ended up as a negative, but you just look at it as like an absolute value of that. And our exact value minus our midpoint gave us that value there. So notice when you look at the absolute values, the midpoint one is about 0.0012 or so closer than the trapezoidal one. So we'll look at two more trapezoidal rule examples. So our width, we'll do 1/2 minus 0, b minus a over 4. Well, that's really like 1/2 times 1/4, so we just get 1/8. 1/8, if you want to think of it as a decimal, is 0.125. That might make our lives easier. So our x0 is 0, x1 is 0.125, x2 would be 0.25. x3 would equal 0.375, and x4 would equal our last part there, the 1/2 or 0.5. So for trapezoidal rule, we'll have 1/2 times our width. We'll have f of the first thing plus 2 f of the second thing. And we'll have 2 for each of these middle ones. And the last part, we'll just have one of them. Now, when we go to plug this in the calculator, again, open a new document. And because we have a trig function, you might want to just double check and make sure everything is in radians when you put it in. So we'll open a new document. We'll go to our graphs page. And we have sine, and in parentheses, we'll have x squared. And we'll just go to menu and settings 9, double check it is in fact in radians. And we'll also go home 5.2 and just double check and make sure it is in radians, so we're good there as well. We'll now go to our calculator page, and we can put in what we had. Now, 1/2 times 1/8, it might save us some time to just put in as 1/16. If you want, you can put them each in individually and multiply them. And we'll do f of our first thing, the 0, plus 2 for our next thing, the 0.125. 2 for the 0.25. 2 for the 0.375. And then just one of them for the 0.5. Take a second, double check, and make sure you have everything punched in correctly with your pluses and your 2's and whatnot. I see all the time people have it written correctly on their paper, but they get the wrong number because they didn't punch it in correctly. And we'll get about 0.042743 or so. And again, what that is that's an approximation of our area under the curve of sine x squared from 0 to 1/2. We'll look at one more case. We'll do this function here. Now, it's important to note in this function what this really is. This is 1 over 1 plus t squared plus t to the 4th dt. So really our function is the 1 over the trinomial there, 1 plus t squared plus t to the 4th. To find our width, we'll do b minus a over n, so we'll get 3/4, or 0.75. x0, 0, x1 is 0.75, x2 is 1.5, x3 would be 2.25, and x4 would be the 3. So we'll have 1/2 times our width of 3/4. We'll just have 1 of the first one, 0. We'll have 2 of the next one, the 0.75. 2 of the 1.5. 2 of the 2.25. And then 1 of the 3. Now again, we've got to make sure we open a new document because we're going to be putting in a different function. Now remember, your calculator only recognizes x's, so these t's we'll have to put in as x's in our graphs page. So we'll go to a new document. In our graphs page, we'll have 1 over, again, we're going to put the t's in as x's. We'll have 1 plus x squared plus x to the 4th. We'll add a calculator page. And now 1/2 times 3/4 will give us 3/8. That can save us some time in plugging in by doing that in our head. So we have 1 of the first one, the 0. 2 of the second one, the 0.75. 2 of the third one, the 1.5. 2 of the fourth one, the 2.25, and then 1 of the last one, which was the 3. And as always, just double check, make sure you have your pluses, make sure you have all your parentheses closed correctly. And we get about 0.89218 or so. And again, that's an approximation for the area under that graph from 0 to 3. That's all for today's video. We'll see you next class, period.